All right, let's pick it up with number 53. And this isn't referencing that table above, which represents the ground state for nitrogen. Right? Remember, the ground state is the lowest possible energy of the electrons around an atom under current conditions. And for our purposes, that current condition is STP, standard temperature and pressure. Standard temperature is 25 degrees and pressure is 1 atmosphere. So if we look at nitrogen, which has 7 protons and 7 electrons, its ground state is going to be 1s2, 2s2, that's 4, we need 3 more, 2p3. But the this is N L. We need M sub L because that's the way it's parsed out there. So if we obey Hund's rule, we put 1 in each orbit. Okay. Shell, subshell, orbit. That means we're going to have, I guess they go complete. So we have these like that. 2, 4, yeah, 7. Okay, so which one looks like that? Looks like A. Oh, they left off the 1s2. Okay, so they were only giving us the valence. They were giving us the valence electrons. And they just left off 1s2. Now, what happens if you add an electron? Where does it go? Well, these are all have 1 spin up, spin up, spin up. So the next one has to go spin down right there. And that would be E. That would be 54. All right, this is 54. All right. Let's have a look at 55. In which group do all the elements have the same number of valence electrons? Right. If the question is the same number of valence electrons, then you look for all the elements coming from exactly the same group. So all you have to do is look at the periodic table, say phosphorus and sulfur. Nope. Phosphorus and sulfur are 2 different groups. So they don't have the same number of valence electrons. That one's out. How about B? Silver, cadmium, yeah. Silver, cadmium, and argon. Well, we know silver and cadmium are not noble gases, so that lets this one out. Right? Argon, they're not in argon's neighborhood. Sodium, calcium, barium. Sodium is an alkaline metal. Calcium is an alkaline earth. Right? Those are 2 different groups. So C is out. How about D? Phosphorus, arsenic. Yep, they're in the same group. Selenium is in the chalcogen group. And phosphorus and arsenic are in the nitrogens. Right? 2 different groups. So D can't be it. That means E is it. None of them. None of them have the same number of valence electrons, all 3. All right. How about 58? Right. 58. The following elements, which has occupied d orbitals in its ground state neutral atoms. Occupied d orbitals. Let's see what we have to work with here. A, B, C, D, and E. Right, there's chlorine, phosphorus, silicon, calcium, barium. All right, if we want to, I would go at it as eliminating the ones that can't possibly have d orbital electrons. All right, so anything from calcium on back won't have d electrons in it. Once you get into here, you have d electrons, and then everything past that has d electrons in it. Right, so we have calcium, right? That one's out. Barium, oh, barium's a good one. Silicon's above, right? So it's out. Phosphorus is out. Chlorine's out. Barium is the only one that has d electrons in its ground state. I see a nodding head. Are you still working on it?
You said from calcium.
Yeah. Calcium back that way, and then back this way, and then back this way. Right. Lesser electrons. Yeah. Okay. 59. Okay. Of the following elements, which needs 3 electrons to complete its valence shell? A completed valence shell is going to be noble gas configuration. So which one is 3 positions to the left? Because that way you would add 3 electrons to the valence shell and end up a noble gas. So we move to the left, and it could be 1, 2, 3. Anyone in this group: nitrogen, phosphorus, arsenic, and ammonia. And if we look to see what our possibilities are, phosphorus is the only one in there. Right. Phosphorus will take 3 electrons to make it look like argon. Okay, to complete the octet. Chlorine only needs 1. Silicon needs 4. Calcium, actually calcium, when it says needs 3 electrons, I assume they mean add 3 electrons. So any of those metals you're not going to add, you're going to lose. All right, that was 59. Let's see, who's next? 62. Which of the following atoms has 3 electrons in p orbitals in its valence shell? 3 electrons in its p orbitals. 3 electrons in p orbitals. Okay. 3 electrons in p orbitals means, well, the simplest would be any one of these would have 3 electrons in its p orbital. So let's see if we got a match there. Barium won't be it. Gallium has only got 1 electron, right? Because it's right here. This is where the p's start. Remember, this is filling the s orbitals, filling the p orbitals, filling the d orbitals, filling the f orbitals. And it's so 1 electron in your p orbital, 2 in p, 3 in p. Okay. So it would have to come from that group, either nitrogen, phosphorus, arsenic, or antimony. Let me see if I'm misreading that. Barium, no. Gallium, no, only has 1 electron. Vanadium, no, vanadium's a transition metal. And bismuth. Oh, yeah. I didn't go down far enough. Bismuth has 3 electrons in its p orbital. Okay. Let's see. 66 and 7. 66. Which of the following is the highest energy orbital for a silicon atom? All right. So we're looking at silicon, and it's got 14. Actually, look where silicon's located. What is the highest energy orbital that's being filled there? This is 1, 2, 3. This is 1s, 2s, 2p, 3s, 3p. 3p, and it has 2 electrons. Right, so 3p has 2 electrons in it, and that's the highest energy. If we wrote the whole thing out, right, 1s2, 2s2, 2p, 6, 3s2, and 3p2. 2, 4, 10, 14. So this is the highest one, and I deduced that by where it is in the periodic table. Right, the highest energy would be here. It'd be a p orbital, and it would be a 3p. There's 1, 2, 3, 3p. Would give me 2 electrons because it's 2 positions to the left, aluminum, silicon. 2 electrons in the 3p orbital. And we don't have to draw the whole thing out unless you just want to. But that tells you the highest energy electron in that molecule, in that atom, excuse me. Okay.
Yeah, it makes sense, like what you're saying does, but how do you do that big long string of 1s2, 2s?
Practice.
Well, can
That's
you
it.
show me like this part right here? This is like on the periodic table, like, so.
Okay. We're adding them in sequence, right?
Yes.
Lowest energy to highest energy. So I'm going 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 3, 4, 5, 6, 3s1, 3s2, 3p1, 3p2.
And then it goes down to like potassium.
And then it goes 4s1, 4s2, and then 3d. You drop down on the 4th period, these drop down to 3s, 3d.
3D what?
3d1,
And then,
3d2, 3d3, 3d4, 3d5, 3d6.
so you don't just like count all those up, they all,
Well, I'm counting them as I go.
okay,
That's how I sequence them out. Now, there are some places in here where the sequence is not what you would expect.
like 4D10, what's that?
So this would be 5, period 5. This would be 4, d10.
And then what would it be?
Then when you go here,
No. So like, say you wanted like silver in this, what would you do?
back up 1,
But in this string,
4d, well, 4d9. But actually, silver is one of those anomalies.
like the exceptions.
Yeah, it's an exception.
Okay,
So-
what about like,
You don't want to know about the exception?
No.
Okay.
what about, is gold an exception?
I would expect it to be, but I'm not sure.
What about lead?
Lead.
Yeah.
Now, lead would be, let's see, 2, 3, 4, 5, 6p2 would be its highest orbital.
62, but the big string and stuff. Would it
Oh,
have
we
a
just
D in it?
have to keep going.
Would it have a D in it?
Yeah. Oh, yeah. It would have a 5d, 10, and then a 6p2. Because this is the 6th. This is 6th period.
Uh-huh.
So it'd be 6s1, 2, and 5d. Well, actually, once you get to this place, when you get here, you gotta go down here and finish those out and then come back up here. So this is gonna have some 4f's in it. Gonna have 4f10. Go from here down there. And that's why I didn't give you these right here, because it's confusing enough to do the S, P's, and D's. We'll leave the F's out for now.
Okay.
But that's the way the periodic table is structured. Right, and you can get a lot of information out of it. 67 next. Okay. Which of the following process represents the ionization energy of bromine? All right, so bromine, when we're determining the ionization energy of any atom or any element, we have to start with the gas. Right? And the reason we do that is because if we start, bromine is normally a liquid at room temperature. If we started from that point, we'd have to add energy to it just to convert it from a liquid to a gas. And that doesn't include promoting any electrons to infinity. Right, so we have to start with gas if we want to learn about the electron movement. Just going from a liquid to a gas is a phase change. It has nothing to do with electrons. Well, maybe it has something to do with electrons, but not ionization. And then we're going to add energy to it, and we're going to end up with the promotion of a single electron for that gas, and there's the free electron. Okay, we've removed the electron from here, and it's a separate product now with this charge +1 and that -1. And then the energy required to do that is an expression of the ionization energy, the first ionization energy, which is 1 electron removed from the neutral atom. So that would be C. C would answer that question. All right, 68. Let's see. Order the elements sulfur, chlorine, fluorine. Sulfur, chlorine, fluorine, based on what? In terms of increasing ionization energy. And I assume what they mean, since they're giving you just the symbol, the neutral symbol, that it's the first ionization energy. Right? That's the only trend we've worked on so far in the on the periodic table. So how does the ionization energy increase? From left to right and bottom to top. So lower left to upper right increases ionization energy. Fluorine is going to have the highest ionization energy. How about sulfur and chlorine? Well, sulfur is down. Chlorine is down also, but it's right below fluorine. And sulfur is to the left and down. So it would have the lowest of this three. So that's the correct order, just as written. This would have the greatest ionization energy. This would have the lowest of the triad, and then that would be in between. Right, sulfur, chlorine, fluorine. How about ordering increasing atomic radii for that same group? How does that trend work? The atomic radius decreases from left to right, correct? Because you're in the same you're in the same principal quantum number, moving from left to right, but you're increasing the number of protons. We call it that the effective nuclear charge is increasing from left to right, which tends to draw those electrons in, right? The positive attracts the electrons, shrinks the atom. So left to right is decreasing, and bottom to top is decreasing. Because as you move down, you get higher energy levels, which means a bigger atom. So from bottom to top, left to right is decreasing atomic radius. So if we're going increasing atomic radius, it would be from upper right to lower left. So fluorine would be the smallest. Sulfur would be the biggest. Chlorine would be in the middle again. Okay. 73. Of the following elements, which has the lowest first ionization energy? We just look at what we got. And the first ionization energy is going to be lowest for metals, obviously. So we can throw out chlorine, phosphorus, and silicon's on the borderline, throw it out. Calcium and barium. Calcium is above barium. All right, so the lower ionization energy is below calcium, that's barium. Barium is in the lower left-hand corner, which is the lowest possible ionization energy. It has the lowest electronegativity too. So barium would be A, right? A would be barium. It would have the lowest first ionization energy. How about 74? Of the following elements, which is most likely to form a negative ion with charge 1 minus? Okay, in this case, you're looking for most likely to form charge 1. We're looking to complete the octet, to complete an energy level, right? And all of these halogens only one electron, and they'll each one will look like its neighbor, noble gas. So we can throw the metals out because they don't want electrons. Barium, calcium, right? Silicon's in between. Phosphorus needs is most likely to form 3 minus charge, because phosphorus add 1, 2, 3 electrons to get to argon. That's when they're most happy. It's when they can get that noble gas configuration. So chlorine is the best answer there. It has a -1 charge. Right. 75. Which of the following atoms has the largest ionization energy? All right, this was an easy one. Rather than struggling with lower left to upper right, just see if there's a noble gas in there. Noble gases don't want to get rid, right? A noble gas has complete atomic shells, which means the noble gas itself is all core. And core is where the energy requirements go through the roof. So neon is a noble gas. It doesn't want to get rid of electron at all. It's going to take a lot of energy to ionize neon. So that's your best answer. If you got a noble gas in there, pick that one for that question. The largest ionization energy. Or if it says second ionization energy, and there's no noble gas in there, look for the one where the second electron to come off is part of the core. So that would be lithium, sodium, potassium, rubidium, right? It's got 1 valence electron. Strip that out. Now you're into the core. Second ionization energy is going to go 10 times higher. That's not the question here, but I thought I'd throw that in for free. 77. Looks like we're regressing. Which has these types of electromagnetic radiation arranged in decreasing frequency? Decreasing frequency. Right. Decreasing frequency to me means decreasing energy. That's the way I think of it. Decreasing energy would be, if we put the highest energy over here would be gamma rays, right? Gamma rays. Then you'd have X-rays. Then you'd have ultraviolet, right? Then you have the visibles, right? Starting with the blues and then on up to the reds. And then you'd have the infrareds, and then you'd have the microwaves, and then you'd have the radio waves. And energy is decreasing from left to right here. And frequency is also decreasing from left to right. So if we're in decreasing frequency, we would go, let's see, let's look, visible, ultraviolet, no, wrong direction. I'm looking at A. A is the wrong direction. B, radio waves, visible, radio waves, visible, that's the wrong direction too. You're going backwards. You need to go left to right, and this the way we've got it set up here. Ultraviolet, visible, infrared. C looks like a good choice to me. And then you can look at the others, but test taking technique, when you find the right answer, go with it. And you don't have any other squirrely ones in there like 2 of the above and none of the above and all that, weirdo stuff. So if that's the case, if each answer is unique, then you work your way down to find the right answer, stop, put it down and go to the next one. That's assuming you get the right answer, right? And you don't sit there and second guess yourself. All right, 78. Looks like we're at it again. Which of these types of electromagnetic radiation arranged in order of increasing wavelength? Well, increasing wavelength is the same as decreasing frequency. So it's the same answer: ultraviolet, visible, infrared. Right? Increasing wavelength is decreasing energy or decreasing frequency. Right? So that was easy. Which of these types of electromagnetic radiation arranged in order of decreasing energy? Same thing. Right? We've already answered that question. Right? We answered 77, 78, 79, all of them in 78, 77. Okay. About 80. In the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which of the properties? All right, sometimes I have to go in here and say, all right, we got this one, we got this one, and we got this one. Spin is easy. This is energy. Right? This is energy level and size. Right? This is shape. This is orientation in space. Okay. So let's see, which one is it wanting to talk about? Where's most, with which of the properties? One there, magnetic orbital momentum. Right? Which one is these magnetic orbital momentum? That one. This is angular momentum. Momentum. Let's see. The symbol for this in physics is that angular momentum. That's the Greek letter rho. And then this one is magnetic. The magnetic is orientation. So that would be B in this case. How about the quantum theory? The angular orbital momentum. All right, now we're going back to this one. L is most associated with shape. Okay. All right. Let's see. Now we're down to 84. Try these out. Select the correct electron configuration for copper. Okay, and we're using the abbreviated version. So copper is over here. Has 29 electrons. And if we're going to use the abbreviated version, you work your way backwards to argon. So we're taking argon as our starting point. And argon's 18. Yeah, 18. So that means we have 11 more electrons to go.
Why are you going back?
Because it's a core. It's a simple way to, if we start with argon's configuration, then we're just adding on top of that. Right? So we would add on top of argon, we would add 1, 2, 3, 4s, 3d. 4s and 3d10. All right, that's 12. Oh, that's too many. So that would be 9, right? I guess I am going to have to show you an anomaly. This is one of those anomalies. Okay, here's how I'm going to explain it. If we did it this way, what are the orbitals of the d subshell? Right, d is what number? Right, s is 0, p is 1, d is 2, right? So 2 means that we can have 5 of these. -2, -1, 0, +1, and +2. We can have 1, 2, 3, 4, 5. D orbitals. Okay, we've got 9 electrons here. We go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Here's the thing about energy. The atom wants to be the lowest possible energy, and that means more stability. And copper is more stable if we take one of these 4s electrons and put it over here and make it complete d orbital. Now this becomes 10 and this is 1. That's an anomaly. Right? So to answer this question, B is the best answer. A is your first assumption, right? 2 and 9. But we know that this is the preferred lower energy state. And that means we steal 1 from here and put it there to make this complete. And the s orbital is not too particular. Plus, this is N is 4 is the bigger, so higher energy level. Okay, so that answers 84. There are others like that. There are other half orbital filling. And so if you have 4s2 and 3d 4, 3d4. So 4s2, 1, 2, 3, 4. Chromium would be that way. It would steal one of those s's and make 5 electrons in the d to put 1 in each of the orbitals. And that would be more stable. So chromium is another anomaly. Okay, deviation, whatever you want to call it. All right, so that answers 84. Let's go to 85. Which of the following equations correctly represents the process involved in the electron affinity of X? Okay, again, electron affinity starts with a neutral atom and it has to be a gas. And electron affinity means accepting an electron. So that means the electron is on the reactant side. Now we end up with a gas with a negative charge, and that's the expression for electron affinity. Now, what would the sign of the energy be? It would be negative, right? If this electron comes from infinity down to the atom into one of its orbitals, it has to give up energy, right? And giving up energy or exothermic reactions are always negative values. All right, 86. Which of the following lists of atoms are arranged in order of decreasing atomic radius? Decreasing atomic radius. That would be from lower left to upper right, would be decreasing radius. So what do we have? We've got lithium, oxygen, nitrogen, fluorine, lithium, nitrogen, fluorine, sodium, strontium. I'm looking at the answers to see which are available. Calcium, cesium. Oops. Calcium, cesium. Don't have sulfur yet. Sulfur and selenium. Oops. Okay, those are our possibilities. Decreasing atomic radius. Which would be the smallest atomic radius in that whole group? Upper right-hand corner, right? Fluorine. That's the smallest radius. Which would be the biggest atomic radius? Lower left-hand, right? Cesium. Cesium would be the largest. Okay. Now let's work from there. what would be bigger than fluorine? Well, to the left, oxygen, nitrogen, sulfur would be bigger. Oxygen, nitrogen, there's sulfur. So oxygen would be the next one, right? Fluorine would be the smallest. Then we'd have oxygen. And then where would you go? Well, I'd go down to sulfur and then to nitrogen. No, sorry. That's wrong. Why is that wrong? Or am I the only one that recognized it? If we go down to sulfur, you're adding an energy level, right? So if we're staying the same energy level, nitrogen should be the next one, the next biggest one. Then we could go down to sulfur unless there's carbon in there. Carbon, no boron, carbon. All right, we'll go down to sulfur next. Right, that's if we start with fluorine, right? So, and they're carrots are the other direction. So we have to flip it around. Put fluorine, oxygen, nitrogen, sulfur. Fluorine. See, fluorine is the least, then oxygen. B, right? B's in there, right? B works. I'm not sure about the others, but that's a perfectly good answer. We don't have any other options, so I'd say pick B. Hey, 87. You get to do some math. Consider an atom traveling at 1% of the speed of light. The de Broglie wavelength is found to be 1.46 times 10 to the minus third picometers. Which element is this? All right. So let's put what we know of here. The velocity of the atom is 1%, 0.01 times the speed of light, right? 1% of the speed of light. 2.9979 times 10 to the 8th meters per second. Okay. And what else do we know? The wavelength is 1.46 times 10 to the minus third. 1.46 times 10 to the minus third picometers. Okay. How are we going to identify the element? Remember, there are only two ways to learn what the element is. Either the atomic number of protons, or the molar mass. Molar mass will get you really close. So I think we're into molar mass here. And I abbreviate that molecular weight. So that means mass per mole. Right, or M over N. All right. So how about mass? Can we get mass out of this? Well, yeah. All we need is, that's if it's light. But this is the equivalent. This is the light equivalence of mass. So instead of C squared here, we're going to have M times V squared. What's the velocity of the object? And then we need energy, don't we? All right, how are we going to get energy? Well, now we need Planck's equation. Energy equals Planck's constant times frequency. Or we got wavelength here, so let's do it like that. So what's speed of light equals frequency times wavelength, right? Right, so frequency is going to be C over lambda. Right, so that'll give us the energy, and the energy will go into this equation. We have the speed, the energy, we can calculate the mass. Right. Now, what's that the mass of? I think that's the mass of one atom. Right. Yeah, that's the mass of one atom. Okay. So we have two options here. All right, we can calculate the energy, then put the energy and mass into that equation and calculate it. Or we can say energy is equal to this, so we take that and put it over here in place of energy, substitution. And then solve for mass. All right, is that too much math? You want to do them step at a time? It's up to you. All right, what would this be? Well, this is 10 to the minus 2, isn't it? So that means its velocity is 2.9979 times 10 to the 6th meters per second. And these have to be in SI units, meters and seconds. This one has to be in meters also. Right? So what's a pico? Let's see. Milli is 10 to the minus 3rd. Micro is 10 to the minus 6th. Nano is 10 to the minus 9th. Pico is 10 to the minus 12th. So if I take this right here and take 10 to the minus 12 meters times 10 to the minus 3rd times 1.46, then that's 1.46 times 10 to the minus 15 meters. That's the wavelength. Good so far? All right. So now, at this point, we're still working on mass. We'll get to moles in a minute. All right, so if we got this wavelength, and we put the wavelength, speed of light, and Planck constant, we can calculate the energy. So the energy is going to be equal to Planck's constant, 6.6 something or other. Have to look it up.
6.626.
That sounds right. Times 10 to the minus 34, right? Yeah. Is that right? 6.626 times 10 to the minus 34. And then speed of light is 2.9979 times 10 to the 8th meters per second. And then the wavelength is 1.46 times 10 to the minus 15 meters. So we can find the energy here. And what are the units of energy going to be? Joules. Joules is the SI standard. So let me get my calculator out. 6.626 exponent. Oops. Start over. There we go. There. That one, and then times the speed of light. And divided by wavelength.
So what is it, joules per second? Or
No, just joules. Energy is joules only. If you use in this formula,
cancel out?
well, the meters cancel out and gives you reciprocal seconds, but then this one has units also.
What's it?
I have to look them up. Useful information. Here we go. Joule seconds. Yeah. Joule seconds. And this is going to be reciprocal seconds because that cancels out. That's in the denominator. This is in the numerator. Those cancel. And we're good. And I get 1.36 times 10 to the minus 10th joules is the energy of that atom. Okay, now we can find out what the mass is. We just have to solve for mass using this part and that part. So that would be mass equals energy divided by velocity squared. So 1.36 times 10 to the minus 10 joules divided by the velocity squared, which is right here. 2.9979 times 10 to the 6th meter per second squared. So what's the mass of that atom? 1.36. Well, it's already in my calculator. 2.9979 exponent 6 squared. Divided into that value. So I get 1.51 times 10 to the minus 23. And what are the units? Has to be SI units. This is kilograms. Right? Okay. So now we got the mass. The molar mass is going to be, let's put that in grams. Kilo is 10 to the third, right? Okay. So that'd be minus 20. Right? 10 to the third plus 10 to the minus 23rd is 1.51 times 10 to the minus 20. Then I'm going the wrong direction, aren't I? If the unit gets smaller, the number has, oh, the number did get bigger. Never mind. That's right. 20 grams. Now we need to find the number of moles. Right? If you have one atom, convert that to moles. 6.022 times 10 to the 23rd atoms per mole. Right? So that's 1 divided by 6.022 exponent 23rd, and let's take the reciprocal, which is 1.66 times 10 minus 24 moles. So now we got the moles. And let's see, they're in, oops, let's see, if I get that fixed. Let's put that around and times 1,000. There we go. Now I need to flip it again in the right order. There we go. Now I can divide. I get 9. Something went wrong. That's a huge number. Let's see where I went wrong. Okay, did I do this right? Velocity. That's 1%, right? 1%, 21. So 10 to the minus 2. Okay, that's right. So if we're calculating velocity, this is picometers. Is that right? Pico is 10 to the minus 12. Maybe it's over here. That's only like this. Micro, nano, pico. That's right. Picometers is 10 to the minus 12 meters. 10 minus 12 fairs, that's 3. That's so if the unit gets bigger, the number gets smaller. That's true. Okay. 1.46, 10 to the minus 30. Did I put the right number up there? It's 10 to the minus 30 picometers. Yeah. Okay. So that one's right. And that wavelength goes in here. That's 15. That actually, that needs to be. No, that's right. I think that's where I went wrong. This needs to be velocity. Not speed of light. Because we're working with an atom, not a unit of. So this needs to be 6. So what would that do to the answer? If that goes down by 100, this should go also smaller by 100, right? Like that. Let's see if that makes sense. What's 15 plus this? 19 minus 19, and then minus 19 and 6. Well, it's got to take that into account. That's better. Okay, so this is 12. minus 12. Now, let's say 1.36. I think I know what it is, but I'm going to calculate it anyway. And then 2.9979 exponent 6 square it. Divide that in. Yeah, this should be 25. And this should be, that's kilograms. So 3 would be 22, right? There we go. So this one's going to get smaller by 2 units. So this would be 91.2 grams per mole. Let's see, 91.2 is zirconium. Is that one of our? Yeah, zirconium. That's where I made my boo-boo. Right. This is fine if you're up against light, but we're up against the velocity of the particle, not the velocity of light. Velocity of the atom. So that's why I needed to substitute V there instead of C. That would be the calculation of energy for a photon. Yep. That took entirely too long. How about 88? See, I'm almost out of time. Right? Is it 145 that we cut out?
Yeah.
All right. We're almost there.
Yeah, we're like 119.
See how many I've got. I've chosen between here and there. The next one on my list is 88. So it's 1, 2, 3, 4. Not going to make it.
That's a new purpose.
That's
a
Yeah. Where were we? 88. Okay, well, we'll go as far as we can, and then we'll stop. An investigation of electronic absorption spectrum of a particular element found that a photon has a wavelength of 500 nanometers, provides just enough energy to promote an electron from second quantum level to the third. From this information, we can deduce. All right, if it's going from the second quantum level, let's see, 88. Draw a picture. There's a nucleus. It's going from the second to the third. Right, and it's absorbed enough energy to give you at 500 nanometers to promote that electron up from second to third. Okay. What can we deduce from that? The energy. What can we gather from that? What can we calculate from that? The energy of the n equals 2 level? No. We can't deduce the n equals 3 level either, because this is internal. The sum of the energies of n equals 2 and n equals 3? No. The difference in the energy between N2 and N3? Yes. That quantized energy from here to here, we can deduce from that amount of energy required to promote the electron. So D is the answer to this one. All right. '89, is it? Based upon that table above, where we actually you are given the energies for each one of the energy levels. In the hydrogen spectrum, what's the wavelength of light associated with n equals 3 to n equals 1 electron transition? If it's going from n equals 3 down to n equals 1, right? It's going to give up a certain amount of energy. And we can calculate the wavelength. What we need is what's the difference from 3 to 1, right? So final minus initial energy, final minus initial would be what? The final is 1. So minus 2.178 minus 2.178 times 10 to the negative 18 joules. And that we subtract the initial, which is 3 minus 0.2420 times 10 to the negative 18. Okay. And that'll give us the energy of that transition. This is not right. Sorry. 2.178. 0.242. That's better. This is minus 1.936 times 10 minus 18. Now that tells us that, well, this is the amount of energy that was given up, right? Because it's a negative sign, we lost energy. But if we're going to calculate the wavelength for this one, we have energy equals Planck times that, or C Planck times C over wavelength. So we have, we only need the positive value. Right, because the transition is going to give us a wavelength one way or the other. Either it'll give up that light or it'll absorb that light. Right, so the sign doesn't matter in this case. And that's equal to Planck's constant. Let's solve it. We're looking for the wavelength, aren't we? Okay. So let's solve it for the wavelength. If the wavelength comes over here and the energy goes over there, that's Planck's C divided by energy. Let's do it that way. Then we can put it all in one calculation. So we need Planck's constant, 626 times 10 to the minus 34 joule seconds. And then speed of light, 2.9979 times 10 to the 8th meters per second. And then energy, which is 1.936 10 to the minus 18th joules. Now, seconds cancel, joules cancel, and our wavelength is in meters. Right? The answers are in nanometers, aren't they? Or centimeters or meters. Okay, so we got several possibilities. All right, so let's take 6.626 (349), and then speed of light. That's that, and then 1.936. This is 1.036 times 10 to the minus 7 meters. So is that one of them? Yeah. 1.03 times 10 to the minus 7. So we didn't have to change the units after all. E is the answer to this one. Oops. Still right? No, we're good. All right. And we move down to what's the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from a 5 to a 1. All right, so it's going to be the same thing. The same process. If the electron goes from 5 to 1, what's the energy change, right? You just subtract the energy from 5 from 1. If it's a negative, you just take the negative sign off and use that as your energy in the calculation. All right, and you should come out with B. 9.5 times 10 to the minus 8 meters. I'm trying to save time here. How about 91? Which of the following is a reasonable criticism of the Bohr model of the atom? Well, let's see. It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Now, that's a valid criticism, right? It doesn't explain why the electron doesn't fall into the nucleus. If it orbits like a planet, then it should. The orbit should decay eventually. So it makes no attempt, which is a valid criticism. We're looking for an invalid. Which of the following is a reasonable criticism? Well, A is a reasonable criticism. B, it does not adequately predict the line spectrum of hydrogen. No, it does that. Wait a minute, let me read that right. Which of the following is a reasonable criticism of the Bohr model of the atom? It makes no attempt to explain why the negative electrons are. Yeah. Because there's a constant pull, right? Positive and negative, it's constantly pulling. It should crash into the nucleus. All right, so A is possible. B's not. That's not a valid criticism because it does predict the line spectrum of hydrogen. C, it does not adequately predict the ionization energy of the valence electrons for elements other than hydrogen. Yeah, that's a valid criticism. Right. So A and C both. Does not adequately predict the ionization energy of the first energy level electrons for one electron species. No, it does that. Shows the electrons to exist outside of the nucleus. That's not a valid criticism. Okay, so what I'm thinking is A and C are both valid criticisms, right? So if that type of question shows up on an exam, you can put either one and be right, or put both. '93. Which of the following statements are true? An excited atom, Roman numeral 1, an excited atom can return to its ground state by absorbing electromagnetic radiation. No, when it returns to its ground state, it gives up energy. All right, so 1 is false. 2, the energy of an atom is increased when electromagnetic radiation is emitted. No, it's decreased. When you give up energy, the atom loses it. Energy of electromagnetic radiation increases as its frequency increases. Yes. That's what Planck said. So 3 is valid. An electron, number 4, an electron in an n equals 4 state in the hydrogen atom can go to the n equals 2 state by emitting electromagnetic radiation at the appropriate frequency. Yes, 3 and 4 are both true. How about 5? The frequency of wavelength of electromagnetic radiation is inversely proportional to each other. The frequency and wavelength. Yes, they are. Right? If we say energy equals, and that's a constant, energy equals, no, sorry, speed of light, wavelength times frequency. Anytime you get a constant equal to a product, these are inversely proportional to one another. Right. So 3, 4, and 5 are all true. That's D. Consider the following representation of a 2p orbital. 94. This is a 2p orbital. All right. Which of the following statements best describes the movement of electrons in a p orbital? The electron moves along the outer surface of the p orbital similar to a figure 8. I don't think so. What is the orbital actually saying? It's saying this is the most probable location for finding an electron. It's somewhere in there. We don't even know how it's moving. That's the general location. So B, the electrons move within the two lobes of the p orbital, but never beyond the outside. Now, this is the most probable. They could be anywhere, right? Very low probability, but they could be anywhere, right? So we haven't found the right one yet. Electrons are concentrated at the center, the node. Well, that's definitely false. What we're saying at the node is that there's no probability of finding an electron there at all, right here. The electrons are only moving in one lobe at any given time. No. So maybe E, process of elimination. The electron movement cannot be exactly determined. That is true, according to Heisenberg's uncertainty principle. If we say we know where the electron is, we can't say how fast it's moving. Or if we know how fast it's moving, we can't say where it is. Right, so E is the best answer for that one. All right, 95. How many electrons can be contained in all the orbitals within n equals 4? N equals 4. So what can we have for L? Right, L could be 0, 1, 2, or 3, correct? N minus 1. Okay, how about M sub L? This could be 0, that's it. This could be 0. This could be, excuse me, this could be minus 1, 0, plus 1. This could be minus 2, minus 1, 0, plus 1, plus 2. And this one could be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. And for each one of those, you can have 2 electrons. Plus 1/2, minus 1/2. So the question is, how many electrons can be contained in all the orbitals n equals 4? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 times 2 equals 32. Maximum 32 electrons in n equals 4. Okay? Yep.
So you just did each number individually.
Uh-huh. Yeah, it's like the roots of a tree spreading out, like the branch. So we can have these for that level. Each one of these could have its branch. That branched here, branched here, branched here, branched here. And then each one of these can have 2 apiece. So it just added up all the possibilities. And that means at n equals 4, we can have 32 electrons. So let's go to our periodic table. Where is n equals 4? 1, 2, 3, 4. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Paint myself into a corner. Let's see, 4, 4. If n equals 4, we have these, we have these. Well, 13, 14, 15, 16, 18. And where did the other 14 go? Oh, 4F. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There we go. Right, because these are all 4s. Right? These are 4S, 4P, 4D, and 4F. I think I was going to be able to talk my way out of that one. All right. Oops, I'm out of time. Let's see. I got quite a few to go, don't I? All right, so I'm going to leave it right there and come back later.
We each scroll down. Hold on.
Yeah. Oh, you just want to get the answers? Okay. 96, 7, 8.
The sheet that you have, that writes them out.
Yeah. It's easier to follow it this way.
Well,
Right.
it's-
6, 7, and 8 are DAA. Okay, and then we go down to 101 is B. One oh four is E. See, 107, 108, B and C. Bravo, Charlie. Uh-huh. I had a student in a class, I think it was last semester. I knew all of them, all the letters. They're military.
I knew Alpha, Foxtrot,
Delta,
yeah, Delta.
Echo,
Echo,
Foxtrot, Golf,
yeah.
Hotel,
Some of them were-
India. J was J. Juliet.
Jupiter.
That doesn't sound right.
Jupiter.
Is it Jupiter? I don't remember. I haven't gone that far yet.
I was that probably won't get had a, this was.
Oh, okay.
And I read through them all, but
Okay.
there's some weird ones though, that you would.
Yeah. Yeah, there are some weird ones.
Some thoughts, there's some thoughts about that, I don't understand what you just said.
107, 108, B and C. Okay. And then is that it? I think that's it. Yep. So I'll tell you what, I'm just going to shut it down. And if you have questions about those that we didn't cover on the board, go to the work problems.
Most of those are pretty easy to follow.
Okay. So I'm going to end the meeting and we're going to go in the lab and titrate.